Hello and welcome. I'm Bill Wake. We're here working on an Elm interpreter. We've been working for a while. We've been working on Infix operators and trying to put them in with a precedence parser. So let's take a look at that again. I think I've rearranged the table, all these rules a little bit since we last saw them, but basically operator precedence, you define, well, it works for certain grammars, which are operator grammars that basically it's like a term, an operator, a term, an operator, a term, an operator, and so on. If your grammar looks like that, then you don't ever have two operators directly next to each other. You don't have two terms directly next to each other. It lets you do this kind of parsing. And the way you do it, you define these relationships between operators. So think about evaluating 3 plus 4 times 5. You want to do the multiplication first, and that's what this is a generalization of. So we have this notion of rules that aren't for the operators, like $ is the end of file, either end, identifier, parentheses, looks like that's it. And then when you have a new operator, you define these rules, how it relates to all those existing things. And then finally, you define relationships between operators, depending on the precedence and the associativity. We've basically encoded all this. Last time we kind of got to the very end and had a misencoding on one of the, I think it was something versus $ rules or something like that. Maybe I had $ less than op reversed, something. But once you have all those rules, you build in, you have a parser that applies them. Okay, and this is from the old Dragon book. It's a pretty simple parsing mechanism. It's known as shift-reduce parsing. Shift-reduce is kind of a general category, but you're basically maintaining a stack, and you can push things on the stack, or you can recognize that some rule has been met and you reduce the stack. And so with this, you're going to go through until you get to the end of file characters on top of the stack, and your input pointer is at the end of the input. You're going to say the stack's empty, the input's done, we're done. Otherwise, it's a process of comparison. We'll pop the topmost terminal symbol on the stack, and then we'll have A is that and B is the character we're pointing to. And so we're comparing what's on the stack versus what's on the input. And if the A is less than B or equal to B, then we'll push it. And then we'll move to the next input. So pushing just puts that thing on the stack, the number or identifier or whatever it is, say, and moves on to the next input. The alternative is if A is greater than B, the symbol on the top is greater than the input, then we recognized, oh, we've actually matched something, and we're going to repeatedly pop the stack until we get a less than to the terminal, a less than from the top of the stack to the most recent pop. Okay, so we're going to pop down until we get to a less than. And once you've done this, you're basically Well, you're trying to match these characters with that, and as long as you get to the top of the loop there in line 3 with an empty stack and an empty input string, then you've matched correctly. All right, let's go to the code. Okay, let's see. Where did we leave off? So we got precedence operator tests. We've got builder tests. And here's our parser. You can see the shift and reduce. And I think the kind of lovely thing about this, there are tricks you can do on the table, and we're not going to get into that too much, but you can fold that table into two arrays of operators, and you can define a comparison function that basically takes a function of the first operator versus a function of the second operator, and that whole n by n table is now a 2n, 2 rows of n for the input tokens input. So it's just an array of ints in the simplest implementation. And then this thing it's a stack of ints and an input stream of ints if you used that for tokens, and all you're doing is like compare two ints and push one on the stack or pop one off and do something. It's a very, you can definitely see how it could map to a very straightforward C or even assembly language implementation that it just doesn't mess around with fancy stuff. It just looks at tokens and relationships, and that's it. Okay. Let's see. So I think what we did, was this our test? A plus B plus C. Well, we ran the tests. I'll run them again just to be careful, but we've got we pass in a list of operators with their precedence and their associativity. So plus is a middling precedence with left associative, because A plus B plus C is A plus B plus C. All right, and we get we're parsing that. It should parse fine, and it does. Okay, so let's see. Now our table, I don't know if we can show the history on that maybe. It's another week I've been bouncing around between environments. Really, that's not, okay, we should be able to do it in here. Test for then. $7 days. We must have pushed in the last 7 days. Well, while that's thinking, let's take a look at our parser again. Okay, so not too deep. We have an input stream that's a list of tokens terminated by end of file. And we do our stack, and then we're digging up the relationship between them and decide what to do based on that. Yeah, and this. Okay, so, well, one thing I'd like to do. One thing is, we're looking forward to semantics. So right now, I think we've almost done this, and I believe this should just work, but we've got to test a little more thoroughly. I kind of want to get a feel for the tree building aspect of this. How do we know what we want to put this in an expression tree, and it's not clear to me where we do that. Well, it's clear in the sense that I think there's only a couple of choices, but what I want to do is just add some, we'll just kind of treat this as a spike, just a manual sort of thing. Input token. Okay. Let's If you're shifting, let's print shift and then the input token. I hope that prints something useful. And if we're popping, let's print pop last popped, I guess. Okay, so let's run our parser test. Well, this would be a good test. What I'd like to see out of this is, and I think what we'll see is a what they call a postfix enumeration. So if you have a plus b, and then above that plus c is your tree, the postfix is a, b plus, c plus. And I think that might be the order we get from this. Let's just run this one test. And we're interested in the print statements at this point. I mean, I want it to pass, of course, but I'm pretty sure we're safe there. Okay. Shift lowercase a, pop a, b, c, ab plus, b plus. Okay, the shifts are not useful, or they're redundant, it seems. Okay. We could make this a little better, but I keep thinking about visualizations for these things, and I don't know. That's another project entirely. And also, I think I don't know if I've said this last week, but I'm kind of thinking April. We'll wrap up this Elm interpreter in April. It won't be done, barring a great miracle in my progress compared to what I've been doing. I don't think it'll be done, but I think we'll have worked through the biggest issues of it. And if we ever wanted to try it again, I'm sure we'd get there a lot faster. All right, so now let's see what we got. I don't know why I ran them all. Let's just run one. Just this one. So it looked like we were seeing everything on the reduce because stuff ends up on the stack as well. Yeah, so lowercase name a, b plus, c plus. All right, now if we did a plus b times c, which I don't think we've done, let's make a new test for that. And I don't know, should not throw is kind of redundant. It does throw if it fails. Okay, AB plus, let's make this times. We need to add the operator. Plus 5 left. Let's add dot star. Not going to help me, huh? Okay, I'm going to say it's star. Precedence should be higher, and it should also be left associative. So this one is the first one up here. This is our table of operators and their precedence and their associativity. This table is it would be a string, but it's really an array for us, an array of tokens. So if you saw lowercase name a plus b times c, we would expect, in contrast to this one, I would expect a, b, c times plus. Okay. And let's a plus b times c. Okay. AB plus, whoops, did I run the wrong one? A plus B star C. Looks like I did. Try again. Yeah, ABC times plus. So the BC times. So what you want to think of for evaluation, this stream is perfect for that. You get an A, you get a B, you get an A, you push it on your stack. You get a B, you push it on. So I should start over. Ignore the word pop there. Just treat this as a program for a stack-based evaluator. And so it's like keystrokes on an old HP calculator. You're going to push A, you're going to get B, you're going to push B, you're going to push C, you're going to do the star operator that takes the last two off the stack and multiplies them. That's BC, B times C, and you put the result back on the stack, whatever they are. And then you get a plus, and that says, well, pop, and you got A on the stack and the product on the stack, and plus adds those two and puts it back on the stack. And then at the end of evaluation, you got one entry in your stack, and it's the resulting value. And that's also easy to make trees out of, which is nice for us. We get a token, we'll push them on the stack, but we get an operator, we pop and make a tree out of those last two things, BC, and push it back on the stack. And then we get the plus, and we pop off the A and the tree of B times C, and we evaluate those, or we make a tree out of those and push it back on the stack. And at the end, we have a tree of expressions. Very promising. Okay, I'm happy about that. Okay. And this is, it's hard to keep the runtime versus the parse time straight, but the parser's job is to match these input streams using the rules embedded in those operator precedence tables. It matches the input stream and tells us, does this thing match? And if so, it doesn't throw an error. We're happy it matched. Yay, But parsing isn't enough for compilers or interpreters. You also have to, you either have to produce some sort of tree, or you have to produce the value you would get evaluating that tree. And we're producing the tree, and then the interpreter comes in later and evaluates the tree. But it's funny. I mean, stacks get used a lot because we're using a stack to keep track of the tokens. Then we're going to use a stack to build up the tree. And then we're going to use a stack to evaluate the tree. So it's like everywhere a stack. Now, okay. The other thing we can do, the question is, what's the output of this, right? Right now, it's nothing. It's just, it will throw if there's an error. And we would like to have the output be a tree, or at least an array of expressions, but a single expression would be nice if we can do that. Now, we could take these prints, and we could make the output of this thing be the sequence of pops, which is really a sequence of tokens. It could be a sequence of tokens ready to evaluate into a tree or to evaluate. And that would be one thing we can do. It depends how much separation you want. Excuse me. The other thing we can do is we could just produce the list of tokens, or produce the tree itself. Now, to produce the tree, that means we'd have to maintain the extra stack in here, but it'll all be done in one step. So it's hard to know what's going to be better for us. I guess we have to do pushing and popping with the tree, right? So what we're going to do with the tree is, if I wanted to replace 42, one thing I could do would be say, are you an operator or a token, like an ID? If you're an ID, I'm just going to push you on the stack, my new stack, my tree maker stack. I could push you on the stack. If I see an operator, I'm going to pop the last 2 trees off the stack. Yeah, so I guess I'd be pushing the tree that goes with this token, and then my operator, I would say, oh, I got to pop the thing, pop two trees off the stack, combine them, and put them back on the stack. It does sound like a bit of stuff. And maybe our result should just be this list of tokens. And this is the tokens matched. Well, they're probably a subset of the input stream. So if we had parentheses, we don't really need to represent them. The tree does that implicitly, so we would be okay without them. But we would filter out parentheses and put the output stream of the result of the tokens coming from the parse. I think that'd be something we could convert to a tree. I think a separate thing to do that would be good. Then this doesn't get complicated. It just has to maintain a list of outputs. Okay. All right. Let's see. What else could we do? I guess I'm trying to think of a moderately complicated expression that would convince us that things are right. How about, well, I know 3 plus numbers are already a problem. Let's see. That's the precedence. This is the parser. I'm going to make another complicated expression, I guess. Okay. Let's make this thing, how about just complicated expression. All right, so we'll have plus, we'll have star. Let's add in exponent, up arrow, precedence 9, and right associative. So we got the option to mix things. So I would like to say A times B star A star B plus how about C to the D to the E plus C, and then times F. Okay, so this expression is A times B plus C to the D to the E times F. All right. And the parenthesized version, what? Equals. Doesn't like it. What? Okay. Space equals. Okay. That's better. I don't know what was going on there. Okay, so if I parenthesize this, it's A times B is definitely higher, plus, I think we'll have to go twice. This is C to the D to the E, because it's a right associative, times F. That stuff, like that. Okay, so A times B, so, and let's let's predict our pop stuff, our print statements too. I think they're going to give us A, B times C, D, E, up arrow. So that's D to the E, C to the D to the E, and then F times plus. Okay, is that right? So in these output streams like this, you definitely should see the same operators and the same operands, but they'll be in different orders. The operands, ABC, will be in, a substring or a what do you call it? Is that a substring where you're allowed to skip around? A, B, C, D, E, F should come out in order regardless. And then the operator's order is all about precedence. So times A times B is definitely the highest first thing we can evaluate. Then we got C, D, E is arrow is C to the D to the E, ES, F times. I don't need commas here. We'll know. Okay, so that's my prediction. And if this passes, then that gives us a lot of confidence that our parser is doing the right thing. Our operator table builder's right, and our parser's right, and the world's all happy. And if it's not, it's going to be painful. Okay, so AB star, CDE up arrow, F star plus. Okay, that is great news. So what it means is we could, rather than being my comment here, we could say that's the job of the parser, is to produce an array of tokens. And let's just go back and modify that. So I think we've got our to-dos. We got some stuff done here. So let's catch that. 0406. This is all still infix operators. Okay, so implement the operator parser to work on token. Yes. Test operator and precedence and mixed operator expressions. We just did a pretty complicated one. So we'll claim both those. And then add semantics. That's what we're doing. I think we're breaking it up into two parts though. The first step is make the parser produce a list of tokens in what do we call that again? It's postorder. Postorder is left, right, and the root at every level. So AB times, all right, C plus. Okay, so we will do that, and that's going to require this thing to return something, but let's start testing it first. Okay, so should not throw an empty thing should get an empty array back. So let tokens equal that, and assert equal tokens that. Yeah, type. I think we'll get this okay when we change the parser. The parser should produce array of token, but they're not in the same order as the input. Okay, and then we'll just put result. Okay, I'm just going to always return result here, and we'll update it. It should complain at the bottom too. Interesting. I don't know why it's not complaining. We might get some complaints that we're ignoring the value. Okay, that's boring. Oh, while true. I guess the only way out is through here. Interesting. Okay. Parse. But this thing passed. Hey, start empty, it's empty. All right, this one now should not throw is even more. Okay. I'm going to call this Postorder. What's going on here? Okay, we'll take that. Assert equal Postorder. It should be the same as lowercase name. And we don't expect the EOF to come out, and that's fine. I don't think we need it. We don't want it. Do I have an extra parenthesis there? Okay. Result of parse is unused. That's not correct. Okay, and this should fail. Okay, we got equals. We expected a lowercase name. And that is easily done here. We will append result.append last popped. Okay, and I'm taking the print out because now we're getting it in our output. We can follow it. Okay, this should pass now. All right, the next one, the error case, we just have a parser with a comma. That's not a valid arithmetic expression, so let's we do want that one to throw the error. That's fine. Now this one, we're going to do similar to what we did. We're going to capture the output and then assert, well, let's make it expected. And this is kind of a reorganization of this, so I will just take that. A lowercase really. All right, and then we expect Postorder to be the same as expected. A plus B plus C should come out AB plus C plus. And this is mostly mechanical at this point. I feel like we established that the complicated expression worked, so I don't expect trouble here. All right, let Postorder equal that. We'll take that same bit of stuff. A plus B times C is this goes to the bottom. A, B times C, BC star should be the case. Okay, and then this goes away. And we'll have the same assertion. I think that's one of those cases where the comment is helpful because this is just such a big expression to work with. I guess I just need this again. Oh no, I should have done that. What have I got? Okay, let's move this down first, so I can see it when I work on this. And now we can copy this. All right, so we expect AB star. Move that down. The plus goes to the end. AB star C, this can go down. This can go down. CDE arrow arrow F. Oops. F star plus, no end of file. Okay, AB times CDE up F star plus. Perfect. All right, and all tests should do that now. Very good. And let's commit this while we're here. Okay, so we made the parser return a post order list of the input tokens. I think that's true enough. All right, let's take a look across things. The error, we need the precedence table coming in. That seems fine. We parse independent expressions. That's okay. True, while true, get the stack token, the input token. I think that's pretty good. We had some tests. They're getting a little wordy with these complicated expressions, but I think they got us through the cases. We had an empty string, we had an error case, well, we had a simple parse, an error case. I might move this one down. I'm just trying to tell. I'm never quite sure if it's better to have the error cases early, but we got the empty string, which is semi-legit. Not, I don't know, probably won't happen, but that's a reasonable answer. We have an error case. Now we work our way from simple to same operator repeated to mixed operators to an arbitrary expression, and everything is good. This is nice. Doing the parsers with TDD helping out is really really nice. You got kind of that proof at each stage that it works. We're stealing, not stealing. We're using a classic algorithm is what we're doing, but it's not like we invented this algorithm based on what we had or anything like that. We basically imitated it out of a book, and yeah, I think that's okay. Alrighty, so let's just run tests. There's just a slight rearrangement. Okay. So I think the next case then is we want something that takes the list of tokens we get back. This result and converts it into a tree according to expressions. All right, so let's add something here. We'll just start with a test. Close your eyes. Maybe I can just like reload Xcode or something, but I don't know. All right, so we're going to do a Postorder to tree. Okay, we'll rename this. Well, I can just type, but oh, this is tests. And oh, the rename did that for me. Interesting. All right. And this test should fail. I'm in the tests. We'll just run all. All right, that runs. All right, let's go ahead and take a 2-minute break. We'll come back. We'll get this Postorder to tree test thing working, and then we'll start hooking it up to the real thing if we can. All right, see you in a couple of minutes. Welcome back. All right, this should be very straightforward. We want to take something that we want to take a list of tokens and we want to turn them into tree expressions using this Postorder approach. And with things like this, well, our possibilities, we could have an empty list, in which case we don't have anything. I think we're going to say that should be an error tree. That you said you were going to have an expression, but you didn't have one. If we decide that's wrong later, we'll fix it. But I feel like you wouldn't get in here unless the parser, actually the main parser, not just the precedence parser, but the main parser has to decide you're some sort of expression. He's not going to do that unless there's something there. So I think it's a bit of a can't happen case. But let's start there. And I don't know, if you think about what we have, and sometimes this perspective is useful, like you have a list, the things that you can get, we could have a variable, we could have variable operator, stuff like that. Let's see, that's the kind of lists we'll get. And from the tree or the parser perspective, this always is operand, operator, and we can use that fact. But let's just take an empty, and I've not been consistent here. Empty list yields error. Okay, I think that's legit. All right, and so we're going to say there's a What are we going to say there is? Well, somehow I want to get a tree from the post order. I don't know what I'm doing here. Converter. It's really this list. Let's just call it a post order. Some list of tokens, empty list of tokens, dot, let's say there's a tree method. Okay, and the assertion is tree should be, and I think we'll pull the expected out. Expected equal error expression. This really is cannot happen. Error messages dot cannot happen. Okay. We didn't default that to nil. Let's do that. Okay, and expected. Okay, so if I give you an empty list, you give me back a tree, and I expect the tree to be an error expression off of that. And we don't have a post order class, so let's make that. And maybe that's what this thing should be returning to us from our parser. We'll decide that at some point. Oops. It has an init, which takes a list in post order. This is token. And it's got a tree, which yields an expression. And let's just return error expression. We can pick anything other than cannot happen. We'll just take that as a dummy return. Let me just close everything else. Okay, post order, taking empty this, and I think we can build. Right, we got unexpected character, and we want internal error should not happen. All right, well, that's easily addressed. Let's go here. I mean, it's a little primitive, but okay. Let's get our next function. This is, I think, well, the var case is easy. So with trees, the real, I mean, this is an implicit tree, but really the two things that happens, you either have a single thing that you're going to push on the stack, or you have an operator and you pop the stack. Okay, so variable yields variable expression. Right, so in this case, let's make a lowercase name x. And we expect to get a variable. And the name is x. Okay. This is a little more complicated. All right, so let's save the tokens. Let tokens type token. All right, now this is, well, this is if tokens dot count is, do we have is empty maybe? If tokens is empty, return this. All right, and that's sort of a guard clause. All right, now well, for token in tokens, do something. Switch token. And case dot lowercase name, let value, well, let name. We're going to do something, and otherwise we're going to do something else. And I think our otherwise is really this. All right, so if we see a lowercase name, we're going to return it. Variable of name. Now this is not a full really. I would have said through each path it returns, so okay, but well, let's just take this again. I think this is even more of a cannot happen. I don't think we can get to the bottom of this stack, right? We're going to read these names and do it. Now this just returns on the first one. We're just passing the test. It's not the real implementation. All right. I guess no. If you got through the tokens lists, no, I guess it takes semantic knowledge to know that you're going to get here. We already blocked out the empty one. If you have any tokens, we're going to return on both paths. But I can understand the compiler not getting it. All right, now let's see. Can we push our stack and put our stack in place? I mean, it's not really justified by the error case, but let's just push this on the stack, and that'll be good. And I think we just used, let's see, our parser. Yeah, we're just going to do the same deal. A stack is just a list that we treat in a stack-like manner. Okay, so let's let stack of expressions. We're only going to push expressions equal nothing. Okay. Now at the end, All right, so here, yeah, let's push this on the stack. So we'll say stack.append variable name. All right, and then at the end, let's return stack.last. And I think we can say it's there. Okay, so now we're going to push it on the stack and then return it immediately. This can't happen, but we'll deal with that shortly. All right, this should still pass our test. That's the real thing. All right, and our next test, this is variable var plus yields addition expression. And I don't know if we even have one yet. Let's let tokens equals, put lowercase x, y, and plus. Maybe this is input. That might make it a little more clear. Okay, var plus var plus the input. Now the expected is, what do we got? Well, we have these primitive functions, but that's a little different. We don't really have an operator expression. So we're gonna have to kind of push this on our little mental stack. Yet another stack. Operator dot plus with variable x, variable y. Okay. We don't have operator. Okay. And unfortunately, expression has a little bit of stuff to it. But let's add it. All right. Now, unfortunately, this gives us obligations. I guess if we go up to expression itself. I don't know how we want to do this. I don't think this will build because operator doesn't know anything yet. Okay, extra arguments. Yeah, so we need an initializer. And well, this is a token. It's really the operator itself. of a token and left-hand side of an expression. I think it's going to complain about equals and so on not being there. Super init, yeah. Extra call. No member plus. Super init. Okay. Let's call super init with elm type dot unknown for now. Elm type has no member plus. Jump to definition. Jump to definition of token. Let's build again. All right, it fails. Not surprised. Okay, so it's it's a double failure. I mean, one is we get an internal error. We don't want that. But we're not getting expression as string. Well, that means we didn't define equality on operator. Let's set this aside. We'll do it the right way here. All right, so if I set that aside, now I need to worry about the operator. Let's add it. I don't know what that did. Tests. Okay, let's make it operator. And we're trying to alphabetize. Same thing here. Okay. Now, I think we want to find somebody minimal. Variable might be a good case. Well, it'll be handy to have a couple of variables around. Okay, and we're going to make an operator. Oh, well, we want operators that are different and the same. Okay, and so what we should have is that operator 1 with variable 1, variable 2 should be equal to operator with operator 1, variable 1, and variable 2. And it should not be equal to, if the operators differ but the variables are the same, Now let's make the operators equal and the variables different. Well, maybe we should make two cases out of this. This one, variable 1, variable 2, variable 2, variable 2. This one, 1, 2, 1, 1. So we're making sure that operator different, first variable different, second variable different between the two cases. So just one difference. All right, and we expect this to fail. Right, so expression as string, yeah, that's not what we want from equality. Variable tests, I think we've seen enough of. Okay, operator, we need to make it equatable. Oh, right, we just override EQ. Okay, other expression, if that thing is not an operator, or well, if it is an operator, we can do self.operator equals other operator, self.LHS equals other LHS, and self.RHS equals other RHS. That means we need to keep these things. So we need a let operator of type, oops, I gotta change that word. Let's just call it op. Op of token, then we'll make this of token. LHS is an expression. RHS is an expression. And we'll need to assign them. All right, and I think this should pass. Nice. All right, next test. Generic type. We're going to say unknown type for now. Variable name. Name. Dot type, elm type dot unknown. I think evaluation, let's just do an error for now. Okay, if our expression is that, evaluate, let's just pass an empty one. And this deserves a better test than we're giving it. Error expression, error messages dot cannot happen. Okay. Let's see. We didn't run this one yet, but I think it passes already. This one should not pass, I don't think. No, it does? Okay. I guess that's the default in the parent. Unknown variable returns error, so that's really an evaluation thing. We're going to ignore that. And then as string, I'm guessing we want to say operator plus variable x. We haven't really defined it. One more parend. Variable used. Nope. Operator plus variable plus name plus x. All right, and that will not pass. And really, I'll take whatever token prints. I might print dot plus or token dot plus or something. And we're just trying to get this thing conforming enough that we can do our post order test. That's really what we care about. Okay, as string. So let's just do operator. And we'll do 1, 2, 3. It's got the weirdest grab. All right, the first one is op. The second one is LHS. The third is RHS. Operator plus, yeah, I can live with that. Plus variable name, variable x. Okay, yeah, it just is this. Yeah, so that's a minimal and operator expression type with minimal support. Failed to commit. Well, that's weird. Let's do that again. Okay, we changed that. Class post order project. Post order to tree tests. Post order Swift, operator tests. That seems okay. Postorder tree test, postorder, operator, operator tests. Operator tests. Postorder to tree test, postorder tests, postorder. Well, that seems all right. Elm tests, operator precedence slash post order to tree tests. Yeah, well, I don't have that. Maybe it's a case issue, maybe. Okay, let's rename this. It's gonna work. Okay. Okay, back to this one. Right. So if well, let's see, does this test pass? There's no way it should. Internal error should not happen, is not equal to operator plus variable xy. Okay, that's a good failure. All right, let's go in here. All right, so now we're dealing with all the operators basically. And I don't know the right way to go, but let's start with plus. Okay, so what we want to do is take the last two things on the stack and combine them. Let's stack dot drop last returns a sequence containing all but the final given number. No. This is. Do I have to reassign my stack? I'm not sure. Okay, so I popped the right-hand side, popped the left-hand side, and now I'm going to push the new operator with token, LHS, and RHS. I don't know if that's going to work. Well, we got two issues, at least. One is, is this well formed? We're sort of assuming it is well formed, so I don't feel too bad about that. But I don't know what happens to this. Does it actually drop it on the variable, or does it just require us to store it again? Okay, so we're running it. Okay, and failed. That's probably a good thing. Post tree. Okay, let's go take a break. And we'll come back and see why our equality failed. Even though we got operator plus working. That's interesting. Okay, we will be back shortly. Welcome back. All right. So we got a operator variable plus variable y. Variable y is not equal to x plus y. Okay. Did we... All right. Our input was x, y plus. Our thing was expected was plus x, y, which is correct. But we got plus y. Interesting. LHS, RHS. Oh, it didn't drop. Okay, let's see if we can do this. I got a feeling that doesn't go. Oh, it's okay. Okay, so it left it at the top of the stack, and I think we'll pass now. Yeah. Okay. Well, believe it or not, at some level we're done. Not at the level of actually being done, but I think let's just do var op yields operator expression. All right, and now I'm going to make let operators equal of type token equal this, and everywhere it says that, I want to make operators dot for each. Is that what it is? This'll we're ignoring it for a moment. I just want to make sure it, oh yeah, it's going to pass because it doesn't have any choice. All right, let's just do plus. I mean, that one didn't run through anything. This time we're running through, but I don't have the operator in. We'll plug in the operator. $0, and here again 0. Okay, so I'm just trying to make it so that we handle each operator, and we're starting with just plus, so we're kind of back to the test we started with. But at this point we want to do all the Elm operators. We have a list somewhere. Let's see. Well, let's take what we got first. We got running tests. So handle post order handles expressions with operators. Okay. Now your tree, all it can be is either, well, it could be variables, integers, whatever, but values of some sort and operators, and they're all coming in structured to be a post order tree. And that's really the only two cases. There's either a standalone item or a post order tree. You have to go through all the lists to get there. But once you're at the end, we'll do a more complicated expression just to verify things. But let's run through the other operators. So plus, minus, and I guess I should find my to do. I'm just skimming for the list of operators. There we are. Less than. Well, let's just get the arithmetic ones. Times. I know times is legit. Come on. Oh, those are multi-character. Well, we certainly have plus, minus, times, divide, and I think we have percent. We have up arrow. Integer divide is // we should be able to find that in our lexer. Yeah, let's find float int divide. Yeah, // Okay. Relationals, I guess the ampersands. Well, let's just look for Elm operators here. And plus, minus, // modulo is the arithmetic ones. Let's make sure the arithmetic ones work. Plus, minus, star, / percent. Most of these should fail. Oops. No member slash or //. Float divide int divide. Okay. Be that way. And divide percent. Okay. If it compiles, the only one we support right now is plus. Okay. 5 times, yeah. Float divide, int divide, minus, percent, and star. Okay. So I don't see any reason to go slow here. Minus plus, minus, star, float divide, int divide, and percent. Okay. Nice. All right. And let's make another test for, well, no, we can do relationals too. Dot. Well, not equal. Double equals. Double equals, not equal, less than equal to, greater than equal to. So that was, sorry, double equals, not equal. Double equal. Not equal, less than or equal. greater than. Right, 6 relationals. I don't know if I can fit these in a way that looks better. Okay. These should fail. Double equals, maybe? Yep. Greater than or equal. Greater than. Okay. Try again, but we expect those 6 relational operators to fail. Yep. And we'll just pull them all. Double equals. Maybe I can pull these in one line too. Double equals non-equal, less than or equal, greater than or equal. Okay, should pass. Nice, okay. Let's go to our next test. Well, we have these booleans, right? Ampersand. Let's find this again. Okay, we got arithmetic, relational, comparable. That's okay. Logical. We don't worry about this. I didn't even know there was an XOR. Ampersand and OR bars. Ampersands were only on booleans? Yeah. Maybe we can do that with... Let's make a variation. Actually, I'm going to do this in 2 separate ones. Okay, var arithmetic op yields operator expression. Var relational op yields operator expression. This one doesn't get these. And this one omits these. Var boolean op yields operator expressions. So we want to do ampersand and var. I think that is going to look okay like that. Okay, now I guess we don't know. X could be Boolean, Y could be Boolean, right? So that is okay, I think. We could have had X equals 3 less than 4. Okay, so inputs and that. All right, so this test should fail. Both of them, yeah. Okay, this, that, and go. Now, normally I'd have to worry about could this line 31 or 33 fail because the stack is empty? And the answer should be that cannot happen. We always produce a valid thing coming through, so it really should not happen. I think even this is a redundant test. The token's empty. I don't think that can happen either, but in any case, all these paths take you through error expression. This one cannot happen. Yeah. Okay. So, in effect, I think we're done. All right. I'm not sure what to go with at this point. Let's find to do again. All right. Parser produces a list of tokens in token and Postorder. We did that. Add semantics tree building. That's what we just did. All right. But notice how lovely that is. I mean, it's pretty simple. You get a token, lowercase name, you push it. Actually, uppercase name should be on that list too. I'm inclined to wait because remember what's happening is we have this recursive descent parser for our stuff at this point, and it does not really know how to handle operators. Like we don't have an operator node until we just added it a little bit ago. And what it does, it just kind of gathers them up as a sequence of expressions right now. I think what it needs to do, well, I think that's fine as far as it goes. What's going to happen is our parser thinks it's operating on tokens. It probably has to operate on expressions. And for a given expression, we may have to map it back to the precedence and so on that we have. We're going to have to see about that. The other one is the parentheses may already be processed, and I don't know if we want to keep that or not keep that. So this, it's easy to say, implement this to work on expression, but it may be a little tricky. Then merge them in. Okay. Should do some stretching. Let's make sure everything's okay. Make post order work for all operators. Cool. Again. Okay, we're going to have to do that the hard way. I don't think it's going to work. No. Okay, stop. Post order. 2 tree tests. That. Let's commit. Now it has the thing it's working for. Let's rename this to X post order tree tests. I'm going to fully commit instead of just renaming it twice in one commit. I had hoped that would work, but I guess it's not fix it, it's work around it. Actually, I think this could just be postorder tests because we just call the class postorder. That was an extraneous comment. Okay, will you work? What? What's the question mark mean? Why are you crazy? Let me commit this one. Let's try to commit this. I will discard changes. Maybe this file exists on my disk. Yes. Cancel. Let's see, where is this thing? Oh my. I guess I have a folder here. Postorder test. So it's only it that's insane. Okay, how about post? What name is it after? Postorder 2tree tests.swift. Postorder 2tree tests.swift. Postorder 2tree tests.swift. Okay. Nothing here. Well, something like that. Okay. Now this thing, hopefully it finds it. Can I add files to Elm? Sorry about the flashing. All right. Let's commit this. It's still a question mark. That's... Okay, now I can delete it, I bet. Delete. Move to trash. Commit. Deleted. Okay. Well... What fun. Okay, so I don't know. I guess I can try and reinstall Xcode. It has upgraded since since this problem flash started, implement the operator precedence to work on expression. Okay, so I think what that's going to require, I guess we're going to have to see what's coming out of this thing. Where's expression function call? I guess we'll go to the parser. It knows something. Okay, expressions goes to expression. If the count is 1, it's a... Well, that doesn't seem quite right either, does it? Plus handle operators. Thanks. See, I think what needs to happen here is... Well, no, expression. Let's see. We'll start near the top. Okay, parse. If you can start an expression, then you're a function call or definition. Okay, which is a bunch of expressions, optionally followed by equals and a bunch more expressions. So you get the first expressions. If you have an equals, you do a function definition. Otherwise, you return, I don't know, partial result. Maybe that's first expressions or something. Okay, we'll ignore the function definition. Now we have expressions. Left-hand side is expression. Okay, so we're building up LHS with a list of expressions. And if we have a bunch of them, we call function call. That just can't be right. Because, well, when you have a function like fn with x and y as arguments, you say fn x y. But once you get a plus sign, you should realize you're not a function call anymore. Unless the plus sign's in a nested parentheses or something like that. So it takes a series of expressions. So function of x and then parentheses 3 plus 4 is a list of expressions, no doubt. Yeah, this is kind of tricky. Parenthesized expressions. Okay. Allows comma expressions because those are tuples. If there's 2 or 3 of them, lambda expressions, if statements. Well, we don't have a lot of time, so let me just spend it. Let's run the REPL a little. Let's get some experience with these things. So let's let function of x, y equal, whoops, there's no let. Function of x, y equals x plus y. So this is a definition. There's expression equals, and then x plus y should be some sort of expression. We think this should be okay, and you should be able to say function 3, 4, get 7. Function 3, get a function back, but if you apply that function to 4, you'll get 7. Now, if I say function of 3 and 4 plus 2, you might think you would get 3 plus 6 being 9. Well, let's do times. 4 times 2 is 8, plus 3 is 11. You might think you would get 11, but I think we'll get 24 or an error. 14. 3 plus 4, yeah, okay. So 3 plus 4, fn of 3, 4 got executed as 3 plus 4, and then that's 7 times 2 is 14. So that tells us that the times is not... this thing is only getting the expressions as far as it goes, But when it sees times, it's no longer looking for a function call. And so we need to make our grammar. Boy, those t-shirts are kind of wild. Let's see. So we'd like to make our grammar I guess our functions, these expressions, wow, I don't know how we'll know. The way this is now, it just accumulates all the expressions. If you have function 3, 4, 5, 6, 7, it's just going in and here's one expression, grabs 3, takes the next one. But this thing doesn't have operators. I think that this is something else, not what we're doing. No, I don't think it works, but it's not what we're after. So I think what we need is something like, I mean, you have expressions, one or more expressions, and then operators, operator, and then more expressions. Another good question for here. Function of 3, 4 times function of 4, 5. So that's 7 times 20. And what is that? 3, 4 is 7. Function of 4 is... Function of 4, 5... I don't know where you get 63 out of this. 4 times 5, 4 plus 5, right, is 9 times 7. Okay, that does work. It does treat those function calls as separate entities. So an expression is really expressions followed by operator expressions, operator expressions. Yeah, okay, so... expression operator, expressions plus, and then this whole thing is kind of a star. All right, so you match expressions up to an operator, then you see an operator. If you see an operator, you match the operator, and then the rest of the expressions followed by operator expressions, and so on. And expression cannot start with an operator, so you don't have to worry about grabbing too much. Okay, I think that's where we'll pick up. We'll, let's see, let's say rework grammar to handle this. And that actually comes first. Oop. Okay, so tomorrow we'll start with that. We'll make our grammar handle expressions with operators. Then we'll see what we can do to make this thing work on those expressions. And what they'll do is these things will turn into function calls. So it'll look like function call operator, maybe variable, value like 3, something like that. But yeah, okay. Next time is tomorrow morning, 9 to 11:30 a.m. Eastern Daylight Time. And we will pick up there. Thanks for joining me today. I hope I catch you in the future. Hope you have a good night. Thank you. Bye-bye.